In this video, we're going to look at quicksort. Now, before we get into how it works, I want to quickly remind you how merge sort works, because these are kind of similar. So merge sort was a divide and conquer algorithm you saw in the previous videos, which worked by taking some input of unsorted numbers, or some unsorted sequence. Let's say we had here 1, 5, 8, 3, 2, 6, 7, 9. And it would take this unsorted sequence and break it up evenly in half here, and then take kind of the first half of our sequence and the second half of our sequence, and then recur on that list. So we'd have on the left 1, 5, 8, 3, and on the right 2, 6, 7, 8. And once we had finished all those recursive calls, we would find, let me just write the resulting output here, we'd find, okay, 1, 3, 5, 8 is the resulting sorted list, and 2, 6, 7, 9 is the sorted list when we're done with that. So when we're finished with our recursive calls to merge sort, the kind of power behind it comes from merging two already sorted lists. Now they're already sorted, but they're not sorted with respect to each other. So we have here 1, 3, 5, 8 in order, 2, 6, 7, 9 in order, but there's no order with respect to the first list and the second list. And this is what quicksort aims to do instead. So we'll see that this is also a divide and conquer kind of algorithm. It will divide our input into different lists. We're going to recursively sort those lists, but in order to make putting those sorted lists back together easier, we're going to maintain some kind of an order so that we have everything on the left side of our list is less than everything on the right side of our list. And how we do that is by selecting a pivot element. So again, quicksort is a divide and conquer kind of algorithm. So it works on the divide and conquer paradigm, but we change our divide step a little bit compared to merge sort. So given a sequence of unsorted elements, we take some element, we'll call it the pivot, and let's say it's this last element here. We'll see later that the choice of our pivot will affect the performance of our algorithm, but let's just suppose we take the last element. We use this as a pivot, meaning this element is going to dictate which elements will be in our left list, L, and which elements will be in our right list, G. So we'll use this pivot item to partition all elements of our sequence into everything which is less than that pivot, everything which is equal to that pivot, and everything which is greater than that pivot. So just one by one, we'll work down each element of this list and compare it to our pivot and then place it into those respective lists, L, E, and G. Then we're going to recursively call quicksort on L and on G. We don't have to call it on E because everything in E is equal to each other. They're all equal to the pivot. So kind of just by themselves, they're already sorted. So we recursively call on L and on G. And then once we finish our recursive calls, then that means we have already a sorted list L, this is what we have here, and a sorted list G, which is what we have here. And we knew already that everything inside of E was already sorted. So once we have each individual list sorted, putting them back together is a little bit easier because now we know that everything in list L is less than our pivot, so we can just place them all first, followed by everything in our list E, which is equal to our pivot, and then everything in our sorted list G, which is greater than our pivot. So we already have an order with respect to each sub-list that we had broken our longer list into. So in our divide step, we partition all elements based on our pivot. We recursively call quicksort on the lists L and G, and then our conquer step becomes a little bit easier. We just place the list L, which is now sorted, first, followed by the list E, followed by the list G. Now our partition step is pretty simple. So we are given our unsorted sequence, and we have some pivot element. I haven't said how to pick that pivot element yet, but say we have a pivot element, maybe we're choosing the last one or something else. But if we have our pivot element, then we can just use this in order to compare every item from our sequence S to this pivot item to determine which list it should go into, L, E, or G. So given this pivot item, we're going to compare the next item in our sequence S. So we'll just kind of start at the beginning and work our way through and compare that item, let's call it Y, to whatever our pivot is. And if it's less than it, we'll put it in list L. If it's equal to, we'll put it in E. And if it's greater than, we'll put it in G. And then return those three lists. And these are the three lists that we're going to work with next. Now, I mentioned already that the choice of our pivot is going to affect the performance of our quicksort. But before we get into exactly how that's the case, let's see an example first of quicksort where we just pick the last element as the pivot each time. So we're going to show how quicksort works, just like we did with merge sort, and we're going to do that by illustrating the execution using a binary tree. So we're going to have that each node of this binary tree represents one recursive call to quicksort. So again, quicksort itself doesn't use a tree. This is just illustrating, visualizing how this algorithm is executed. And we're going to have the unsorted sequence kind of on the first side. This is one recursive call. As a result of calling quicksort recursively, we divide this into kind of parts. We have the lists L and G we're going to show here. And then when we're finished with our recursive call, we'll have the sorted kind of output on the right side. So let's see how this would work. Let's say we're given the sequence 6, 3, 5, 8, 2, 4. And let's just suppose that we always choose this last element as our pivot. So we're going to go through and partition this sequence into the lists L, E, and G. So we'll have, using 4 as our pivot, the lists L, E, and G. So we'll compare 6 to 4, which is 6 is greater than 4, 3 to 4, 3 is less than 4, so we've got 3 is the first item in L, 6 is the first item in G, 5 will go in G, 8 will go in G, 2 will go in L, and then 4 is the only one which is equal to 4, so we'll kind of keep that there. But since we're not making any recursive calls on this list E, we're just going to kind of hide that here. So now we recursively call quicksort on the list L, which is 3, 2. It's not yet sorted, but we know that everything in L is less than everything in E, which is less than everything in G. So having that kind of order up front, or semi-ordered elements, will help us to merge them back together easier later. So now we recursively call quicksort on L, and we're going to pick again this last element here, 2, as our pivot. So when we form the list L, E, and G, nothing is less than 2, only 2 is equal to 2, and 3 is the only item greater than 2. So this is our list L, it's empty. 2 is the only item in E, and here's our list G. So L is already sorted because we have no items. G by itself is already sorted because it just has one item, so we're finished with those recursive calls, and now we can merge them back together. So how we merge these together, we take everything in L, which was empty, there's nothing there, followed by everything in E, this is just our pivot, followed by everything in G. So we've got 2, 3. Okay, now let's finish our calls to the right side here. So this was our other list. 6, 5, and 8. Again, we're choosing this last element as our pivot. So we've got L, this is everything less than our pivot, everything equal to our pivot, which is just 8, oops, and everything greater than our pivot. And there is nothing greater than our pivot here. So now we recur on L. So 6, 5 is our list L. We take the last item as our pivot. We have everything less than our pivot over here, everything equal to our pivot, this is just our pivot, and everything greater than our pivot over here. So these two lists by themselves are already sorted, so we're going to put them back together. We have everything less than our pivot comes first, everything equal to our pivot, which was just our pivot, and everything greater than our pivot, that entire sorted sequence. Okay, now we've got kind of to form, working our way back up this tree, to form this sorted sequence, we have everything less than our pivot here, which we place first, followed by everything equal to our pivot, which was just our pivot, followed by everything greater than our pivot, which was empty. Okay, now this gets a little bit more interesting the larger our sequence is. So to form our resulting sorted sequence, we've got now everything less than our pivot. This is kind of working our way back up here. Everything less than our pivot comes first, everything equal to our pivot, which in this case was just our pivot, and followed by everything greater than our pivot, that resulting sorted sequence that we have. So the running time of quicksort is dependent on the pivot that we choose. Now, if we could show that this evenly broke our sequence in half each time, we could say that this runs in n log n time using the same kind of argument that we did for merge sort. But the problem here is that how our sequence is broken up is determined by what our pivot is. Maybe we pick a bad pivot. Maybe it doesn't break up our sequence evenly. So in the worst case, we choose a bad pivot each time. And this would occur if our pivot happens to be the unique minimum or maximum item. So for example, if we happen to choose the minimum pivot each time, then we would have that our list L is empty. Our list E would be that single pivot that we chose. And our list G, if we ended up picking the minimum item, would be all of the other elements in our list. So we start off with n items, and then we remove our one pivot, which is the minimum, the unique minimum, and then we end up with n minus 1 items. And then maybe we're unfortunate, we picked the unique minimum again, and we're left with n minus 2 items, in which case, every time we make a recursive call, we only decrease the size of our list by 1. In this case, our running time would be proportional to however many elements we're working on each time. So in this case, even our partition step alone would require n, big O of n time. And then to partition this sequence would be n minus 1, to partition this sequence would be n minus 2, and so forth, which brings our total running time to the sum of the first n numbers, which is quadratic. And unfortunately, if we were to choose the last pivot each time, this happens when our list is already sorted. So this isn't what we want to happen. This is kind of the worst case situation in this case is to sort our list of elements is when our list is already sorted. We could show that this worst case situation occurs when we select any fixed element. So even if we picked the middle element as the pivot each time, we could create some sequence so that that middle element, whichever one we pick, is the unique minimum, for example. So we could choose this list. So every time I'm constructing this so that the next middle element that we would choose would be that minimum. So this would be a bad example for if instead of choosing the last element or instead of choosing the first element, we chose the middle element, we could still construct a bad sequence where it would give us the worst case running time. So if we use quicksort using a deterministic pivot, so this means that every time we always choose the first one, or we always choose the last one, or we always choose the middle one, or the 2/3 down the list element, if we choose this deterministically, so we have some fixed element which is always the pivot, first, last, middle, whatever, then our worst case running time is big O of n squared, and we can't do any better than this with a deterministic quicksort algorithm. But we'll see how we can get a better average case running time if we introduce some element of randomization, which you'll see in the next video. So if you have any other questions, post on Piazza, let me know, reach out.